So thanks for joining me to listen to my monologue on a lecture where we are discovering a little bit more about doped semiconductors this time. So essentially what we will be doing here in this very lecture is that I will try my best to generalize our treatment from the intrinsic semiconductors that we have just previously treated into doped semiconductors. So essentially extrinsic semiconductors. And specifically, we will in the beginning start by a so-called n-doped semiconductors. And we will show in here in this lecture how this intentional addition specifically into pentavalent elements into silicon. And then these pentavalent elements will be called donors. How this addition of these impurities can dramatically increase the number of electron states we have in the conduction band. So let me repeat. We intentionally dope our silicon matrix and we dope the silicon matrix by pentavalent elements, and these will be called donors, and this will in essence dramatically change the conductivity of our semiconductor. And in order to try to quantitatively understand the process and get some estimates for actual changes in the conductivities, we will use a Bohr's model. You may recall Bohr's model for hydrogen, and we use that to estimate roughly the energy levels that are associated with these donor impurities. And once we know how these impurities behave, then we can understand how we can really change the electron conductivities. So how we can really make or in a way donate electrons into the semiconducting silicon matrix. And this is then, in essence, we will donate these electrons into the conduction band. And then when the electrons are in the conduction band, of course, they will be happily moving around, swishing, swoshing inside in the conduction band inside the material, and then they will give rise to a macroscopic conductivity for the solid. So this is what we will do in essence on this very first lecture regarding doped semiconductors. So, as I promised, we will generalize our treatment, and we will now unravel all the glory of using doped semiconductors. And what this semiconductor doping means, like I already said, we intentionally are adding impurities into the intrinsic semiconductor matrix, and this in essence will change the conductivity of the semiconductor, and it will change it quite dramatically. So as an example, I believe this is from Kittle's a magnificent book on solid state physics. If we add a 1 boron atom per 10 to the power of 5 silicon atoms, this fact increases the conductivity already 1,000-fold. Of course, the trick here with these numbers is that we are actually making this estimate at very cold temperatures, so at cryogenic temperatures of temperature equal to 3 kelvins. So this is the trick that we were doing in order to land with this estimate, so that the silicon at such cold temperatures does not really have that many electrons in the conduction band. So even a tiny addition will increase the electrical conductivity quite dramatically, as we can see here. But nevertheless, this is true, and this is a very good point why we want to actually intentionally start doping our semiconductors. And these small amount of impurities we are placing into the semiconductor matrix, this does not yet really change the overall electronic band structure. So what happens is that we can really rely on the calculated band structure, and we just change slightly the amount of conduction electrons, or vice versa, the amount of holes in the valence band, as we will see in the next lecture. And for ease of mind and conceptual clarity, here we do not consider a general case, but we just restrict to a specific semiconductor, here silicon. But of course, the treatment applies for all the other semiconductors out there. So this is just to make things clearer in when we are choosing a specific material to work with. And as we know, silicon, it comes from the carbon group. It has a valency of 4, and it crystallizes also subsequently into the diamond structure. And now we start placing doping atoms, dopants or impurities into the silicon matrix. And what we will consider here in this lecture is that we consider that we are adding pentavalent elements. So essentially arsenic, As, or phosphorus could be added, or antimony, Sb, into the mix. And this is what we will be considering. And the case where we have trivalent elements as impurities will be considered in the upcoming lecture. So what happens is that this dopant atom, it really replaces a single silicon atom somewhere, and what will be left is that one dopant valence electron will be essentially becoming a free, and then after the accommodation of this dopant atom, the actual like nucleus of the atom into the lattice of silicon, then we will really be having this one extra free electron roughly lying around that can really move around, participate in the formation of the conduction band's number of electrons. And this is a picture that often is used to explain what is happening. So we are adding, in here case, for example, arsenic into the silicon matrix. And of course, for simplicity, I do not consider the diamond structure in full 3D case. I'm just drawing it in a 2D plane. So please remember that the silicon naturally does not form this kind of cubic lattice of two-dimensional form, but rather it forms the diamond structure. So basically 2 atoms in a FCC lattice. And now we replace a single silicon atom with arsenic, and then since it's a pentavalent element, 1 electron is left free, and it's denoted here. So this is then the kind of free electron that can move around freely after the accommodation of arsenic into the silicon lattice. And this will be what happens. And then energy-wise, the B figure tries to elucidate what happens there. And now what's happening is that we don't change much the actual band structure of our silicon semiconductor by placing just a few impurities here and there, so that the majority of silicon atoms are still forming this crystalline structure, and subsequently, of course, we will have the electronic band structure being formed. And now with that, what this arsenic atom actually does, it kind of acts as a donor state, and then depending on where it is with respect to the conduction band or valence band, then it can either give away an electron, or it can absorb the electron if it would be closer to the valence band. But this is essentially what we will be considering here. So please look into the pictures, and once they start making sense to you, you are on the winning side of this scheme of doping semiconductors. It's not that complicated process, but it takes a while for you to kind of grasp what's happening here. So when we are calling these impurities and this configuration, that when they are pentavalent elements doping silicon, then these impurities are actually called often donors. And this process of doping silicon with these kind of impurities is called N-type doping. So donors the impurities are called donors because they, in a way, they donate a single electron into the conduction band. So they add a single electron into the conduction band. So they donate one there, and that's why they're called donors. And N-doping, because N refers to the electron states, the concentration of them. And let's now make a simple calculation. And this calculation is meant to provide us an understanding how we could estimate what would be then the concentration of electrons at the conduction band after we have added these donor impurities. And we want to estimate first the energies with respect to the lowest energy of the of the conduction band, because this energy difference can be then used to estimate how many of these donor states actually are giving 1 electron to the conduction band. So we want to estimate the energies that are associated with this accommodation of the donor into the lattice. And what we want to really estimate is that how much of energy we need to essentially ionize the final leftover, the 5th electron of arsenic, because once that happens, then we can really see that we have a 1 free electron that will essentially is residing in the conduction band. So we want to calculate the ionization energies, because that provides us an understanding of how easily this 1 final 5th extra electron will be raised into the conduction band. And if we will have an electron in the conduction band, of course, macroscopically, that will give rise to a electrical conductivity through the semiconductor. And here we will consider a kind of simplistic picture, and this is often used, is that we consider this donor state to be something resembling the quantum mechanics associated with a hydrogen atom. So we are just interested in a kind of single electron's response, the energy ladder it forms with respect to the environment. And after our dopant has accommodated into the lattice, what we have is that we have this arsenic core. It's a positively charged core, and this will loosely bind the fifth electron within itself. And please, in this state, I would like to also remind you that please recall the earlier treatment we had regarding the screening of the electric field, especially when we were treating that in our section metals. But here also we could see what's happening, that there will be also some conduction electrons nearby, and their slight movement nearby the arsenic donor atom can start screening the positive charge of that, and in the end we can still have a conduction band formed. So this is also what's happening under the hood in this picture, but we don't much say about this fact happening. So we don't really consider the fact that once we are having these positively charged arsenic cores in our matrix, we do not consider that they would markedly affect the movement of the conduction electrons. And let's now make our quick calculation. And like I promised, we will generalize the Bohr's model for the hydrogen atom. And essentially what we will be modifying it by just making a few changes into the approach. So here we are considering arsenic, and what we are considering is that we are not considering arsenic in vacuum, but rather in a dielectric medium. So please recall it's surrounded by silicon. So instead of using the vacuum permittivity in the calculations, we will use the permittivity of our dielectric medium. So this would be our permittivity for silicon. And of course, the dielectric constant of a material, that can be also written using the relative permittivity, so epsilon r, times the vacuum permittivity epsilon naught. Another thing that we change in our Bohr's model is that now the dopant atom really is in a periodic crystal, and this implies to us that instead of a normal electron mass, we should actually consider the effective mass. So that's what we will also be doing in the model, the calculation. So we take the electron's mass, and since we are treating a periodic system, we change the electron's mass to be the effective mass of the electron. So these are the small changes that we make into the model, and this allows us to kind of estimate quite accurately, in fact, the ionization energies. So now the ionization energy simply becomes ED. It's the ionization energy of a form that we have on the denominator, the electric charge to the power of 4 times the effective mass divided by 2 times 4 times pi times the relative permittivity times the dielectric constant of vacuum times h bar, and this inside parentheses squared. And for the case of silicon, we have the effective mass for a electron. It's roughly 0.2 masses of a free electron, and the relative permittivity is 11.7. And now when we plug in the numbers and we compare these estimates with the kind of normal energy, ionization energy associated for a pure hydrogen, and this of course is the 13.6 electron volts. What we get here for the case of arsenic is that in fact we have a dramatically smaller value for ionization energy, so 20 milli electron volts. So what we have physically here, we are calculating ionization energies, and please, this, you probably remember this is the kind of amount of energy we need when we want to take the electron out from a hydrogen and just totally free the electron. So in essence, we want to ionize the hydrogen. And here we are essentially trying to do the same thing, but now we have arsenic as an impurity dopant atom inside a silicon matrix. And now this value tells us how much of energy we need to ionize the arsenic. So we to remove the fifth electron totally away from the arsenic. And when that would happen, then this fifth electron could readily be acting as a free electron. So in essence, it could be residing in the conduction band. Of course, somebody might disapprove our approach because, of course, this is quite simplistic. If we would make a better calculation, we would get something around 30 millielectron volts as a value for the ionization energy. And if we would do the experiments, we would get somewhere around 50 millielectron volts to be the value for this case of dopant. So actually, in fact, we're not that bad. We're not that far away from the kind of better estimates or actual experimental values. And this is fine for us. At least this tells us roughly what's happening, and it gives us reasonable values and an easy approach to also try out the approach for different semiconductors. If we would move away from silicon, let's say, for example, to a gallium arsenide or germanium or silicon germanium dopant alloys. So now we're back into this picture I already highlighted. And here, essentially, what we have is that we could also consider that we would dope the silicon with other kinds of elements. And of course, there are many possibilities for doping with pentavalent dopants. And this is, of course, these are called donors. But the end result would be the same. So roughly, the ionization energies will be similar in magnitude as with the case of arsenic. So this estimate doesn't really depend that sensitively on the kind of actual dopant atom, but rather is mostly dictated by the properties of the silicon matrix. And the interesting thing here, like what this ionization energy now corresponds to, essentially it corresponds to the distance, how far the donor state is from the conduction band. So this around 20 millielectron volts, 30 millielectron volts, or the experimentally measured 50 millielectron volts, it's this difference between the donor state, the arsenic, and the conduction band's minimum energy value. And why this is important is that when we are changing the temperature, or sorry, let me rephrase, when we are considering the temperature of our semiconductor. And please remember that in a room temperature, the kPt value is around 26 millielectron volts. This is now close to the ionization energy value that we just calculated. And what this means physically at these donor states, this fifth electron that was in a way extra after the accumulation of the arsenic into the silicon lattice, these can be very readily excited. And with excited, I mean they can be readily ionized away from arsenic atomic core, and then they can be acting as conduction electrons residing in the conduction band. And this process already happens at room temperature quite readily, because the kPt value of room temperature, 26 millielectron volts, is quite close to the ionization energy we just estimated. So this is the main thing I wanted to teach you for today and during this lecture, so that we now understand. But simply enough, by just adding some impurities into the semiconductor, so essentially making a doped semiconductor, we can quite easily increase the amount of electrons in the conduction band. And this is what happens. And if you would be interested in looking at things from the point of view of the Fermi level, or the chemical potential when drawing here, please note that when we are starting to add donor states into here, and subsequently at room temperature, we start to have a quite considerable population of conduction electrons inside the conduction band, the Fermi level will also be raised accordingly. So it won't be residing anymore roughly midway of the valence band and conduction band, but rather the Fermi level, the chemical potential will be raised closer to the conduction band. Because by definition, that level is where we have the kind of population is midway. So of course that changes when we increase the number of electrons in the conduction band. So this is what I wanted to say. And in the next lecture, we will just make a no-brainer generalization or extension of this approach to acceptor impurities. But more on that in the next lecture. Thanks, and please stay tuned.